Alright, this is part 4 of the final review, and we are looking at logarithms, and we're on problem number 47. So for this problem I have log base 3 of 1 over 9, and we're going to solve this. So in the format that it's in, I need an extra part to rewrite it as an exponent. So I'm going to go ahead and write this as equal to x. Then I can take the 3 and say 3 to the x power is going to equal 1 over 9. So 3 to what power equals 1 over 9. And you can fiddle around in your calculator and try to figure out what x is going to be, or we can do a little bit of rewriting. So I'm going to take this 1/9, I'm going to rewrite it a little bit. So 3 to the x, well 9 is the same thing as 3 squared. So if I rewrite it like that, and then 1 over 3 to the second power is the same thing as 3 to the negative 2 power. So once I get to this format, it says 3 to what power equals 3 to the negative 2. So the x and the negative 2 have to be equal to each other. So that gives us our solution. So 3 to the negative second power would give me 1 over 9. Number 48. I've got log base 16 of 1/4. I'm going to go ahead and write it as equal to x so that I can complete my change. So this will be 16 to the x power equals 1/4. And I have kind of the same situation I did last time, except for it's a little bit reversed. So 16 to what power gives me 1/4? I can play around in the calculator, or I can try to rewrite this a little bit. So I'm actually going to rewrite on both sides. I'm going to write 16 as 4 squared. And 1 over 4 is the same thing as 4 to the negative 1 power. So what I have now is 4 to the 2x power equals 4 to the negative 1 power. So the fact that they're equal tells me that 2x has to be equal to negative 1. So if I divide by 2, then x has to be equal to negative 1/2. So if I wanted to check myself in the calculator, I could say 16 to the negative 1/2 power and make sure that the answer that I get is 1/4. And it should be. Okay, number 49. I have log base 2 of 8. I'm going to write it equal to x. Then I'm going to write this 2 to the x power equals 8. And I could try it in the calculator, or I could try to work it out in my mind. So I'm thinking 2 times itself, how many times will give me 8? So x has to be 3, because 2 times 2 times 2 would give me 8. And then I have one more like this, number 50. Log base 7 of 49. So I'm going to start off by setting that equal to x. And then again I'm going to rewrite it. So 7 to the x power equals 49. And then I just ask myself, what will the power have to be? 7 to what power gives me 49? Well, 7 to the second power would give me 49, so x has to be 2. So that's solving logarithms. And now we're going to do some expanding. With problem number 51, we're going to start with log base 3 of 3x, and we're going to expand it. And basically when I expand it, I'm just trying to spread things out and make sure that I just have one term with each logarithm. So I'm going to have log base 3 of 3 plus log base 3 of x. Because since 3 and x are multiplied, I changed that into two logarithms added. So that's the expansion for number 51. For number 52, I have log 2x divided by 5. So I'm going to break apart the biggest part first. I have 2x divided by 5, and division will change this into log 2x minus log 5. And it seems like I could be finished there, except the 2 and the x are multiplied. It's 2 times x. So if I'm going to break that apart, I'm going to change it to log 2 plus log x, and then minus log 5. So if I have 2 times x divided by 5, then that's going to break into 3 parts. For number 53, I have log base 2 of x squared over 4. So again, I'm going to start off with the biggest chunks. I'm going to break x squared divided by 4 into log base 2 of x squared minus log base 2 of 4. If you work these problems and the base confuses you, then take it out and just pretend like it's not there. Okay, so again, it seems like I'm done, but I'm not quite finished because this is x squared. And anytime you have a power, the power can be moved to the front. So this becomes 2 log x minus log 4. And if the base number doesn't bother you, then you can always just write it back in there next to the bottom of the g. Alright, one more to expand. Okay, when you first look at this problem, it looks like there's a lot to it. So if you take it in steps, it's going to work out a lot better. So I'm going to start off, first of all, by changing this to log base 5, 2 square root of x, minus log base 5, y to the third power. Because I can go ahead with that and separate my fraction, make it a little bit easier. Now for the next step though, I have 2 times the square root of x right here, and so since this is multiplication, I'm going to change it to log base 5 of 2 plus log base 5 of the square root of x. And I can also, in this step, go ahead and take this 3 that's an exponent and write it as minus 3 log base 5 y. Okay, so this seems like it's finished, and it's not a bad answer. It's just that we have one more thing to simplify. The square root of x is the same thing as x to the 1/2 power. So if we rewrite this as x to the 1/2 power, then the 1/2 power can be moved to the front. So log base 5, 2, plus 1/2 log base 5, x minus 3 log base 5, y. So when it's expanded, there should be no powers, there should be no roots, everything should be just spread all the way out as far as it can. That makes an expanded logarithm. And then for number 55, if it's already expanded and they ask us to condense it, then we're going to put everything back together and take it back down to where it's one single logarithm. So log 3 plus 1/2 log x minus log 5. And so when I do this type of problem, I always look for anything that's a coefficient of a logarithm first, because those coefficients are what are going to be moved back to the power over here. So I'm going to do that first. I'm going to keep everything else the way it is, log 3 plus, now I'm going to change this to log x to the 1/2 power minus log 5. Alright, then in my next step, I like to just start with 2 terms at a time. So if I have log 3 plus log x to the 1/2 power, well, addition is going to change into multiplication. But I want to condense it down, so remember this is only going to have one logarithm. So we're going to have log once, and then it's going to be 3 times x to the 1/2 power. And I haven't done anything to that minus log 5, so I'm just going to leave it on there. So we've gone ahead and condensed it down to 2, and now we want to go the final step to condense it down to 1. So since this is subtraction can change into division. So I'm going to have 3x to the 1/2 divided by 5. So now we have one single logarithm. That's a good answer. If you don't like that x to the 1/2 power, it's okay to write it as log 3 square root of x over 5. Either of these answers is going to be just fine. Number 56. Still condensing. We're going to take log 4 plus 3 log x plus log y. Again, the first thing I look for is a coefficient that's going to need to be moved. So I'm going to move that 3 back over here. Log 4 plus log x to the 3rd power and now I'm just going to combine these together. Since addition becomes multiplication, I'm just going to multiply this twice. So I want one single logarithm, and then I'm going to take the 4 and the x to the 3rd and the y, and those will be multiplied. So 4 times x to the 3rd times y. That 4 didn't turn out very good. So now what I've done is I've condensed this down to a single logarithm, and it's easier to move it around. It's kind of like you're packing up your moving box. Okay, one more. Number 57, we have log 2 plus 3 log 3 minus log 9. So, first thing, I look for coefficients. We're going to move the coefficient back here. So I'm going to have log 2 plus log 3 to the 3rd power minus log 9. Since I have addition and I also have subtraction, I'm going to do it in 2 steps. So I'm going to go ahead and start with the first 2, and I'm going to change that addition into multiplication. So it's going to be log 2 times 3 to the third power minus log 9. So that's going to be subtraction changing into division. So I'm going to have 1 log, and I'm going to have 2 times 3 to the third power, and that's going to be divided by 9. And that is a good answer. I would be more comfortable simplifying it, so let's look and see what this would be. 3 to the third power would be 27, and we're going to be dividing by 9. So 27 divided by 9 is 3. So we're left with log of 2 times 3, which is just 6. Okay, so here we are at 58, and for number 58 and for number 60, these two problems, I'm going to show you a slightly different way to solve it than we did before. It's not a big difference, but it will actually make it a little bit easier for you. Alright, so I have 5 to the x power, which equals 12, and I cannot get to this x because it is an exponential. So to get rid of the exponent, I have to use a logarithm. So what I'm going to do is I'm going to use ln. Okay. Once I do that, then that allows me to use this logarithm rule that moves the x to the front. So now it becomes x times ln 5. And then to get the x by itself, I'm just going to divide by ln 5 on both sides. So this sets it up so I can go straight to putting this in the calculator. And I'm going to use 3 decimal places. So I'm going to have ln 12 divided by ln 5. And I'm going to get approximately 1.544. When I worked this problem before, I used a little bit different logarithm, but I think this will make it a lot easier. Alright, number 59. This problem already has a logarithm. So just like some problems we worked earlier, we're going to change the format. So I'm going to take this 3 and do 3 to the second power equals 2x minus 5. So 3 to the second power equals 2x minus 5. By rewriting it, that gets rid of the logarithm completely. So now I can say 3 squared is 9 equal to 2x minus 5. Then I'm going to add 5 to both sides. So 14 equals 2x. Divide both sides by 2. And so 7 equals x. So my solution is 7. Problem number 60. We're going to work this the same way we worked problem number 58. So we have 3 to the 4x power equals 27. And the problem that I have is that I want to get to that x, but it's in the exponent. So I have to use a logarithm to get it out of the exponent. So I'm going to start off by using ln on both sides. You may remember or you may not remember, but ln stands for natural log. Now that it's a logarithm, I can move the 4x to the front. So it makes it 4x times ln 3. And then I can divide by ln 3 on both sides. And I can go ahead and get a decimal for this one. Ln of 27 divided by ln of 3 is actually just going to be 3. And then to get x by itself, I'm going to divide by 4. So my solution is x equals 3/4. Number 60. Oh, no, 61. Sorry. Number 61 is our last logarithm equation to solve. We have log of 7x minus 4 equals log of 2x plus 11. And this is a problem where we're looking at it and we're trying to see what are our options. Both sides have a logarithm, and since they're equal to each other, then that means that the inside part of each logarithm has to be equal. So 7x minus 4 has to be equal to 2x plus 11 because we know that the log is already equal to the other log. So basically all we've done is drop the logarithm off, made this into a normal problem. So I'm going to subtract 2x from both sides, which is 5x minus 4 equal to 11. So now I'm going to add 4 and get 5x equals 15. And then when you divide by 5, you get that x is equal to 3. Do one. For numbers 62 through 65, we're looking at domain and range. Domain is how far does the graph go left to right, like the x-axis, and range is how far does the graph go upward and downward, like the y-axis. So the domain is generally with the x variable and the range is with the y variable. So for number 62, looking at my domain, my graph looks like this. Actually, that's not a very good graph, but it goes more like this. But if I look at this, it's going to the left and it's going to the right and it's not going to stop. So that means that all real numbers work for my domain. That means that any place I go to, I'm going to get different x's and different y's, but I can go as far left and as far right as I want to go. So for the range, now I'm going to look at my same graph and see how far does it go downward and how far does it go upward. Well, if I follow this graph, it's going to go up forever. And if I follow this graph on this side, it's going to go down forever. So again, that's going to be all real numbers. Okay, number 63, we are going to have to kind of interpret this a little bit. The graph itself looks like this, and then it's got arrows. But because of its shape, what we're going to have to assume is that it does the same shape again, that it kind of continues on. So if that's true, then we'll have a little bit different range. But if you talk about the domain, how far does this go to the left and how far does this go to the right? Well, it goes on and on and on and on. So that's going to be all real numbers. But in the graph on the page, there is actually basically a highest point and a lowest point. And we're going to go ahead and approximate that. So like there's a highest point for this graph and there's a lowest point for this graph. It only goes as high as about 3.2 and it only goes as low as negative 3.8 maybe. Now just from looking at this graph I can tell it's really supposed to go from a height of 3.14, which is pi, and the lowest point is supposed to be negative 3.14. So if we wanted to write it that way, we could say that our y value is between That's how we say y is between. And y is going to be between 3.14, which is pi, and negative 3.14, which is negative pi. So we can write that as our range. Now, if you got these numbers wrong, you would be okay. You just want to get as close as possible as you can. All right, for number 64, this graph looks like a sideways parabola, which we have done. So when we do our domain and our range, when I look at this graph to see what the domain's going to be, it's only going to the right, and it's only going to the right. So there is a furthest point to the left that it stops at. So it starts at the y-axis, so that means our domain starts at 0, and then it goes only to the right, so all of the other values are going to be greater than that 0. So you could either say it goes from 0 to infinity. That would be okay to say if you wanted to. Or you could say that it goes from 0 and everything else is going to be greater than. Oh, not y, x. So I could say 0 is less than or equal to x. Or you can say it goes from 0 to infinity, and either way you feel comfortable writing it is okay. Now when we look at the y part, it's only going to the right, but the y values are actually going up, and they're going to continue to go up as we go. And the y values are also going down on this side, and then it's going to continue to go down. So there's not going to be a stopping point for the range, which means the range will be all real numbers. All right, one more. Before we go on to 65, notice that I have 0 is less than or equal to x. I could have also written that as x is greater than or equal to 0, and it would still be right. So both of those ways would be okay. Okay, the last one, number 65, that'll be the last one for this video. It's a big O ellipse. We've done this very, very recently. So really all we have to do is see what are my endpoints from left to right, and what are my endpoints from least to greatest, top to bottom. So for the domain, my x's are going to start at -6 and go to +6. So I'm going to write this as x is between 6 and -6. And then I'm going to write that my range, y is between, and the y values up here are 2 and -2. So y is going to be between 2 and -2. So that's the domain and the range for that ellipse.